afternoon, everybody. My name is Woody Wingfield. I'm the Director of Development for the School of Architecture and the Executive Director of the School of Architecture Foundation. I am very pleased to welcome you this afternoon to today's webinar, The Future of Sustainable Architecture, Biomaterial Construction. As we've done in previous Zoom-based webinars, if you'd like to submit questions to the panelists, you can use the Q&A function at the bottom of your screen throughout the presentation. We'll be watching those and then start to present questions at the Q&A section. We'll try to answer as many questions as possible as time allows after the main discussion. I believe Kate will drop a link to a giving site since we are in the middle of our spring challenge at the School of Architecture. Thanks to all who have given at this point, and hopefully many of the others will join us in supporting the work that our faculty at the School of Architecture are doing, just like Katie MacDonald and Kyle Schumann. At this time, I'd like to invite both of our panelists to turn on their cameras so I can introduce you. Great, thank you. Hi, everybody. Katie MacDonald on the left is a licensed architect and is an assistant professor of architecture at the University's School of Architecture. She's also co-founder of After Architecture and director of the Before Building Laboratory. She's also co-director of the Hemp Co-Lab at UVA. Her scholarship reconsiders construction standards and materials in light of new life cycle questions and in the face of overextended supply chains. As director of the Before Building Laboratory, she pioneers new biomaterial assemblies with the aim of creating building material systems that sequester carbon and reduce construction's contribution to the environmental crisis. Katie is co-founder of After Architecture, an architecture firm named to convey the built environment's impact on culture and ecologies. After Architecture has completed projects in New York, Pennsylvania, Massachusetts, Vermont, Washington, D.C., California, and Europe, including a memorial in Washington, D.C., and an installation at the Oslo Architecture Triennial in 2019 called Enough, the Architecture of Degrowth. For her work at After Architecture, Katie has been recognized as Next Progressive by Architect Magazine, Emerging Designer in the Virginia by Design Awards, and Curbed Young Gun by Curb National. Very cool. Kyle Schumann is assistant professor of architecture at the University's School of Architecture and also co-founder of After Architecture. With a focus on material cultures and public space, After Architecture has completed projects in, I said that before, we'll go ahead and jump ahead. Schumann received his Master of Architecture from Princeton University, where he was awarded the Princeton University Fellowship, and he also holds a Bachelor of Architecture from Cornell University, where he was awarded the William S. Downing Prize for Architectural Design. He is the recipient of the Robert James Idlitz Fellowship and the Robert A.M. Stern Architects Travel Fellowship, which investigated material cultural identities in Alpine Europe as manifest through modernism in the work of Otto Wagner, Jose Plesnik, Edvard Revnikar, and, oh boy, Eduardo Gellner. Schumann's current research leverages technology as a mediator between material quality and authored design intent. He has pioneered several robotically controlled pneumatic forming systems, including air forming and pillow forming. His work has been supported by institutions including the American Institute of Architects and the Center for Architecture, and he has been published in venues including ACA-DIA, CAA, DRIA, ARCC, and ACSA. I think I actually got that right. Ladies and gentlemen, our featured speakers, Katie MacDonald and Kyle Schumann.
Thank you, Woody, for the introduction. We'll just pull up our presentation here and get started. Great. So good afternoon, everybody. It's a pleasure to be here with you all today. As Woody mentioned, I'm Kyle Schumann. This is Katie MacDonald, and we're happy to join you from the School of Architecture, where we serve as assistant professors. We're particularly excited today to share with you a body of work that we've been developing for a while, which leverages material properties to make sustainable buildings. Specifically, our work aims to address the built environment's contribution to global carbon emissions by creating material assemblies from renewable materials that sequester carbon. So outside of our appointments as faculty at the University of Virginia, we run the professional practice After Architecture, a studio named to convey the built environment's impact on cultures and ecologies. Through this practice, we've completed permanent works ranging from furniture to public art installations. So here you see a variety of those earlier projects. We've always been interested in making things physically and thinking about the materials that are used to produce our work. We've also completed permanent works at larger scales, including a public memorial in Washington, D.C., a mountaineering shelter in Europe, as well as private residential projects.
As a complement to our professional practice, we co-direct an academic research lab at the University of Virginia. The Before Building Laboratory pioneers new material assemblies to advance circular construction practices. Working with a team of paid student research assistants, we leverage new technological advancements that enable us to work with natural materials in new ways. This work often takes form as a combination of small material prototypes, material testing, and demonstration assemblies. While small-scale investigations, they have large-scale implications with the potential to disrupt global reliance on concrete and steel as primary structural materials. The work we present today will include building projects from our practice, as well as material research from our labs. So we'll begin by asking, why does sustainable construction matter? Consider the fact that the built environment currently accounts for 39% of global carbon emissions. Will that share increase as 2.5 trillion square feet of space is constructed by 2060? This is the same sum as the entire global building stock today. So we're going to double the building stock in the next 40 years. Buildings equivalent in size to Paris are built every 5 days. A large share of such construction will be built in the developing world and global south. Closer to home, even North America builds 1 million new single-family homes every year. Industrialization and the spread of the international style saw the deployment of concrete, steel, and glass across ecosystems and geopolitical boundaries. In the process, building traditions that made use of locally sourced renewable materials declined. Such materials were considered less sophisticated, predictable, and permanent, as well as more labor-intensive. In essence, they were more difficult to work with, and professionals were less comfortable guaranteeing their performance. Today, construction techniques which economically source and deploy renewable building materials must be resurfaced and advanced. Architects and builders must become comfortable knowing, working with, and leveraging the unique qualities of grown matter. The work that we will share today draws from pre-industrial techniques as well as develops new applications for renewable carbon sequestering materials. New and recent technologies allow us to reimagine traditional constraints on material economies and labor to advance the accessibility of computational construction techniques and to leverage democratize technologies in the process.
So understanding the embodied intelligence of natural materials is a central idea in much of our work. We'll begin with an anecdote that asks you to consider your assumptions about wood construction. Specifically, we'll consider 2 ways to straighten a log. And since industrialization, we believe that answer has been somewhat universal across cultures and societies. It's been to subtract or to transform the raw arcing forms of the tree, which balances its search for light water and other factors into a sort of simple orthogonal prism like the 2x4 that we see on the right. To break wood down into a uniform element produces waste and consumes energy in the production of what is still essentially a raw material in terms of building production. Through this process, the intelligence of the grown material is lost, so we trade greater embodied energy and waste for ease of construction on site. The humble 2x4 is optimized not for material economy or material intelligence, but for human labor and speed of construction. And so this then expands to encompass an entire range of sequential construction practices and building products. So you see the kind of standards in this illustration having to do with the assembly of the wall and everything down to the kind of pickup truck. Beyond industry, standardization practices were embraced by modern architects. In this images here, you see a 1931 exhibition called The Dwelling of Our Time. This is an exhibition put on by Lily Reich and Mies van der Rohe, and it displayed full-scale prototype homes that you see on the left, surrounded by displays of the materials and products from which the houses were produced that you see on the right. And those materials were displayed on this mezzanine that ran around this sort of large aircraft hangar space in which the houses were shown. So this exhibition created a blatant association between the industrial materials and processes used to produce those materials and the modern design that the materials produced. And it was neatly packaged for consumption by a public audience meant to describe the relationship between these materials and modern architecture. The introduction then of computer-aided design brought the potential for more economical applications of custom forms in construction, while extending and reapplying subtractive methods to now create custom form from standardized material. So you're still taking the intelligence of the tree, simplifying it into boards or sheets of plywood, for example, and then reprocessing it through digital fabrication methods to produce sort of custom forms in variable architecture. If we consider the embodied intelligence of the material, we find what we argue is a more favorable approach. In the work of artist-architect Alan Wexler, you see a piece here by Wexler called Reframing Nature, in which he makes incisions into the wandering trunk of a tree and slips wedges of wood into its mass to redirect the center line of the tree into a straight path and transform it from this curving form into this sort of straight linear form. So this is an additive operation that maintains the trunk's taper, the protective skin, and its efficient surface area. So it's a totally different way of straightening the log than the subtractive methods we were looking at. We can also consider individuals like Andy Goldsworthy, whose wandering line of logs seen here in San Francisco leverages the curvature of the material and begins to address this question. So he intuitively systematizes natural materials and phenomena in the service of a singular artistic vision. And we like to think of this process as a collaboration between designer and found grown form, in which you're kind of choosing material specifically to fit different parts of this form so that there's a relationship between the material as it's grown and how it's used to produce this, in this case, this sort of artistic spatial installation. So essentially, we want to ask why straighten, which is to say standardize the log. This question informs our opportunistic approach to leveraging material qualities and behavior. Today, we'll present 7 tactics to harness material intelligence in construction.
So the first tactic will be thermal mass on a suburban house prototype called Domestic Wall. So architect, theorist, and scholar Raynham Banham wrote a kind of important piece called A Home is Not a House in 1965, which presented a critique of American housing and its reliance on environmental control systems through the study of Philip Johnson's Glass House, an iconic work of modern architecture. This project, Domestic Wall, revisits Banham's critique and definition of the environmental bubble in order to reimagine the modern house archetype. The American approach to domesticity has long favored informal conditions, sheds in the landscape. from the original American homestead archetype to Philip Johnson's brick, slab, and fireplace ensemble. Today, increasing resource scarcity, impact concerns, and the growth of cities necessitates a single-family dwelling type that can accommodate greater density, use passive methods of environmental control, and promise Americans the access to nature that they crave, while dislodging the assumption of and desire for a sprawling yard. So the resulting dwelling type accommodates greater density, uses passive environmental control, and promises access to nature. Inverting Johnson's centralized brick service core, domestic wall allows for the neighboring wall between properties to become thickened and house programs such as bathrooms, fireplaces, storage, and frees up the central space of the lot as a courtyard. The building's brick perimeter absorbs solar heat during the day to keep the building warm at night. From the street, passerby glimpse a garden through an opening in the wall. A wooden porch slides out, hugging the sidewalk and providing a perch from which occupants can survey the street, engaging in neighborly camaraderie. Inside the wall, circulation snakes between pipes, services, and storage. Dwelling spaces line the garden and exchange glances through the filter of the lush planted space that lies in the middle, the courtyard. Next, we'll move to tactic 2, material treatment. Located in Northeast Washington, D.C., the Camp Barker Memorial responds to the landscape of American monuments that valorize performance in battle, instead taking form as a series of spatial markers which convey a complicated history. The memorial was designed and commissioned in early 2017 and completed in 2019, a period in which the role of Civil War monuments was being reconsidered. The project advocates for the significance of counter-narratives. The Camp Barker Memorial answers a brief for the design of 3 entry gateways to an elementary school, by framing and revealing the site's history as a Civil War era contraband camp. A typology specific to the Civil War, the contraband camp came into being as a Union establishment, where those escaping slavery sought refuge from Southern enslavement. Initially constructed as Union barracks, Camp Barker later became a contraband camp. Residents experienced cramped, poorly ventilated spaces, food and clothing shortages, and poor sanitary conditions, working for meager wages. However, occupants also gained access to education and religious gatherings. In the aftermath of the war, the site gave birth to a longstanding African-American community just blocks from the heart of the Capitol. The Camp Barker Memorial takes shape as a series of thresholds integrated into the fenced perimeter of a public elementary school. The site, which encompasses an entire urban block, is bounded by the linear school to the north, while fencing on the east, west, and south sides encloses the school grounds. The grounds also double as a public park. The memorial portals introduced in this project simultaneously address the history of the site and its recreational grounds. Intervening in each of the 3 fenced elevations, the memorial takes the monument off its pedestal and puts it at eye level, physically and visually accessible to the public, a series of thresholds that visitors must pass through to enter the grounds. The entry portals recall the informal timber buildings of Camp Barker through wood-clad structures that allow for passage and shading. A continuous folded plane forms each portal's floor, walls, and roof. On the playground side, smaller side wings create habitable spaces that engage the scale of the child. A liner of brass invites reflection and casts a warm glow. Standing within the portal and looking into the brass surface, one can view the outline of one's own reflection and surrounding colors, a kind of visible ghost that removes personal identity in favor of a shared human condition. In contrast to the white marble monuments that define Washington, D.C., the exterior surfaces of each portal are clad in charred wood, a finishing technique which fortifies the material against UV, fire, insects, and other environmental agents. Integrated into this palette are a series of narrative bas-relief sculptures by artist Vinnie Bagwell, which more overtly convey the site's themes. The recessed sculptures, cast of blackened bronze to match the wood, are set into the thickness of the folding portals and depict key figures, moments, and texts in African-American history. The Camp Barker Memorial germinates the site's contradictions for emotional impact. The memorial beacons the elementary school. Abstract space frames narrative sculpture. Charred wood folds over a thin brass liner. Realities that might not readily coexist are forced to do so. The daily diversions of contemporary school children play out on a site where people once sheltered from captivity. It is contrast that makes the memorial a critical part of the elementary school campus. Present-day students may daydream of the children that learned on these grounds a century and a half prior, confronting the promise of emancipation, but a long road to equity ahead. That fight is visibly ongoing, and the memorial a reminder of what is at stake.
We'll move on now to tactic 3, off-grid, and talk about a project we call Hearth, which is an off-woods cabin sited in a kind of remote wooded site in Orwell, Vermont. So in starting the project, we were interested in engaging with the cultural memory of a cabin. What do you think of when you think of a log cabin? And we identified a series of elements: the chimney, the porch, the stack of firewood, and distilled those components of the classic backwoods cabin and rearranged them into a kind of seamless exterior. We think of it as a domestic chimney. So Hearth hybridizes all of these elements through a series of layers as you move from the outside to the inside of the structure. Contrasting the vertical timbers of the surrounding woodlands, the building takes form as a horizontal layering of lumber from the slatted facade to the logs it stows. Here you see a kind of early rendering of our ideas for the project, in which you can see this deep rain screen facade system, which allows the storage of firewood to happen seamlessly sort of around and across the faces of the building, in contrast to the woods that surround the site. And here you see a kind of detail of that rain screen facade built in reality. You can see how it sort of slides off the roof and then becomes the walls. So this system of storing firewood wraps the entirety of the building. The idea is that this facade would then change with the seasons and register the kind of storage and consumption of firewood across the year in a sort of seasonal cycle. Born from the woodlands, the cabin is thought of as an occupiable hearth. It's both built of and fueled by the surrounding timber. Our next tactic moves on to living material, and we'll share a couple of examples. The first is called Grow on Me. It's a table that integrates plant life into the everyday rituals of working and dining. A series of flower pots are nested into cylindrical table legs, giving the illusion that they've been extruded directly from the floor and merging the pot of the plant with the surface of the table. The round geometry of the legs supports a collection of square tabletops, allowing them to pivot from one another and dislodge traditional seating layouts. Grow on Me supports a range of activities, and its cast of botanical characters influences both the appearance of and experience of the table. Vegetation height, variety, and geometry allow for various scenarios, including foliage screening or a shared canopy to join occupants sitting around the table. It's finished in a creamy terracotta in our nod to the materiality, traditional materiality of flower pots. We also, through living materials, want to ask, how do we move from a model of purpose-built to purpose-grown? And so through this, we'll share an example here of the parklet chair, which is a collaboration with barley seeds grown hydroponically into shaped molds. Here you see a few examples of these 3D printed molds in which the seeds are grown. So they're manipulated throughout growth to shape the direction of the gravitropic roots of the barley and the heliotropic sprouts. So the roots are growing in relationship to gravity, the sprouts are growing in relationship to light, and we can control those different aspects of the system to help collaborate with the plants and control the nature in which they're growing together. The chair self-assembles through the interweaving of these growing roots. So it takes form as a landscape displaced from soil, water, and sun, and resituated into the interior. The seat of the chair that you see here is made of nothing but grown barley that's then nested into the wooden legs below. There's no adhesives or other materials used in the production of the seat of this chair.
The next tactic 5, focuses on materials which are local and abundant. The use of material which is local and abundant is central to the construction and composition of Homegrown, a project exhibited at the Knoxville Museum of Art. The first material input for this project is air. Construction formwork is materially intensive and expensive, often resulting in wasted materials, including spent lumber and spent foam. Such waste can proliferate in the construction of customized digital forms in which each mold's geometry is specific to a surface and can therefore only be used once. This technology, which we developed for this project, pillow forming, leverages the abundant and globally available air to create an adaptable system that allows the surface geometry to be highly controlled via a digital workflow, eliminating the use of wasteful single-use molds. The machine consists of a rigid plywood surface and a grid of 1-foot cubic inflatable pillows made of vinyl that can be inflated individually. The flexible top surface of each pillow is attached to neighboring pillows, such that when they're inflated to different heights, they create a single and continuous surface, against which material can be cast or formed. The second material that we'll look at in this project that's local and abundant is invasive species. Homegrown expands the inventory of grown construction materials to species which are not cultivated and harvested, but in fact removed as an act of remediation. The project focuses on the poster child of invasive species, the vine that ate the South, kudzu. The installation entangles discrete parts, including kudzu, bamboo, and landscaping waste, into 4 wall panels, which form an exterior room. These panels are formed using the pillow forming machine. Read alternatively as a ruin or a topiary hedge, Homegrown repositions the aesthetics of digital construction, replacing the smooth, crisp machine assemblies synonymous with the digital turn with an architecture that is fuzzy, fluffy, furry, or shaggy. In this next project, the next local and abundant material that we're interested in is grass. In this project, we're working with colleagues Marek Pindera and Jose Gomez in engineering and Deborah Lawrence in environmental science to analyze material capacities and select grass species which will optimize carbon sequestration and minimize environmental impact. This project is funded as part of UVA's 3 Cavaliers initiative, which encourages work across disciplines. After harvesting and evaluating various species as well as testing methods, we seek to develop applications for grass building components that marry the precision of industrialized paper tubes with the structural intelligence and flexibility of branching geometries. The resulting system has been piloted as a large-scale branching model, as well as small-scale prototypes, and has culminated in the construction of a single bay of a modular, full-scale structural system in which many bays could be aggregated to form a field, a structural field.
Tactic 6 is going to get into several projects. We call this from nose to tail. And so we like to look beyond architecture in the built environment. So in the food world, eating from nose to tail means that you're kind of consuming or making productive use of all the common parts of the animal, as well as the less commonly consumed parts, such as kidneys, liver, heart, tongue, etc., and even using the bones to make bone broth. So the ethos is really to kind of use as much of the material as possible to minimize waste and create useful product from a sort of set amount of material. So in some ways, the timber industry has kind of figured out how to take this from nose to tail ethos and apply it to the tree. So 48% of harvested timber is deemed unfit for construction in its whole form, and it's often shredded down and composited with toxic chemicals to make kind of plywoods or MDF products, or it's burned for fuel production. So this makes the timber industry both highly efficient in its material usage, but also it involves a lot of extra energy inputs. You add these sort of toxic chemicals to the mix. And if wood is burned, it's releasing its captured carbon back into the atmosphere. So in the next series of projects, we explore expanded applications for wood outside of the kind of traditional timber pipeline, or material and wood that's unfit for traditional lumber production. To this end, we're engaging with a lot of sort of digital technologies, specifically the process of twinning, which refers to the creation of digital doppelgangers or kind of 3D computer models of physical artifacts and physical material through both 2D and 3D imaging technologies. So this technology isn't very new. Here you see an image from 1991 from Frank Gehry Technologies, using a 3D pantograph to digitize a model of the Walt Disney Concert Hall. So the technology is not new, but it's becoming increasingly accessible in low cost and low data formats, which allow us kind of all to use these tools and to use them in new ways. So if traditional project delivery involves the creation of design documents long before material is ever acquired, these tools allow us the potential to leverage 3D imaging techniques to inventory material inputs, which will allow design processes to progress in dialogue with material, or to take the qualities of the material into account much earlier in the design process, not just sort of at the end through the construction process. So the first project we'll share in this realm is called Tangential Timber, which is a pavilion that pilots an application for nonlinear wood. Rather than cutting the wood lengthwise to produce boards, the project develops an application for cross sections of wood called timber cookies in the lumber industry. We didn't come up with this term, I wish we did, but the timber industry has all these amazing words for everything. So in this case, we're using cookies. The wood for this project was sourced from a campus stockpile of trees that were either felled by a storm, or cut down due to disease or due to construction projects on grounds. And we worked really productively with the group UVA Sawmilling that gathers this wood that you see here up on O Hill. And we sourced material from this stockpile working with UVA Sawmilling and facilities. And we cut altogether 164 cookies using a mobile bandsaw sawmill. And the cookies varied from about 3 to 5 inches thick, and they were in a variety of different species, just sort of whatever waste material was available to us. We then developed a custom low-cost, low-data workflow to document each of these cookies, each of these pieces of material, so that we could use them into the design. And so instead of using kind of data-intensive or expensive 3D scanning technology, we used only a single photograph of each of the cookies. Here you see a grid of those photographs. The black dots in each corner surrounding each cookie are points that were used for us to calibrate the scale when we sort of brought these into the computer and automatically traced and scaled them and used them to produce 3D models of each of these pieces of material. We then created a test assembly that consists of a compression vault. So we modeled this vault in the computer, and then we used various computational techniques to aggregate these cookies across that form. So the two diagrams you see on the right are showing a sort of flattened version of this structural shell, in which cookies are sort of aggregated across it, larger cookies on the outside or the bottom, smaller ones at the middle or top of the structure, and they were pulled together with controlled overlaps so we could make joinery to determine the placement of each unique piece of material in the drawing that you see on the right. Joinery was then cut with a 5-axis CNC water jet over in the engineering school. This sped up the fabrication process, meaning that we had to kind of minimally cut or reduce each part and able to produce these geometries. And it also limited our cut geometries to ruled surfaces. So it means we're cutting all the way through the material with this high pressure jet of water with an abrasive kind of garnet in it that actually cuts through the material. We built custom jigs in order to cut this material. This is not normally what you do with a water jet, and the jig that you see, this frame and clamping system, we used both on the CNC water jet and on the more traditional 3-axis CNC router, which we'll talk about in a second. So seen here is an initial joint prototype using a puzzle piece logic. So this technique first emerged through a student project at UVA, which is a studio I taught a couple of years ago. And joinery necessitates that the connections that secure these cookies could be possible with the kind of range of different sizes and geometry of the material. So here you see a kind of test joint. This is a photo of the front and back side of the same two cookies joined together. So there's a dovetail connection that allows them to slot together and notch together. But on the other side, you get this kind of shingled appearance, and the actual geometry of each of these pieces of wood is used to inform the geometry of this joint. So the joints are entirely unique for every single two cookies that are coming together using the kind of information that we had from our kind of 2D imaging to 3D scanning process. We then sort of deployed this in a mock-up wall to test how the assembly would come together. It worked pretty well. And so they kind of held together and could be placed vertically in this orientation. And then knowing now that this sort of joinery system would work, we moved on to producing a kind of timber vault as our sort of final demonstration of this system. And the timber units are doubling as both structure and ornament. Here you see the kind of surfacing of these lines across the surface. And those are actually the structural stress lines that are kind of informed from an analysis of the shell. So it's a sort of visual indication of how forces are traveling through the material. The lines double as a graphic pattern for aligning wood masonry units. So it's a kind of massive 3D puzzle when you have to actually put this thing together. And those lines are actually determining also the thickness of the material. So where the lines are denser and more structural forces are present, we can actually thicken those cookies, and where the lines are sparser and less structure is needed, the cookies become thinner across this surface. Altogether, we hope that the work demonstrates a construction process that could be adapted to a global supply of unused material, nonlinear timber. While the prototype vault assembly is a small-scale investigation closer to a pavilion than an enclosed building, it demonstrates structural performance and inhabitability and suggests possibilities for larger architectural applications, including structural walls, vaults, and even non-structural, expressive, aesthetic, or spatial applications. Another project using timber is called variable sawmilling, building off of the last project. We're working on developing tools that allow us to use different types of nonlinear wood. This project, similar to the grass project Katie discussed, is funded through the UVA 3 Cavaliers program, and we're working with mechanical engineer Gavin Garner and environmental scientist Manuel Lordau here at UVA to develop tools that will allow us to mill logs along their natural curvature. We tested this approach By taking low resolution digital scans of a series of logs, this image is what you kind of get as the sort of representation of data that is then mapped onto a 3D form in the computer. And we mounted a commercial bandsaw to a robotic arm to test how we could cut this material in non-linear ways. The 3D scans were used to guide the saw's toolpath, making it possible to precisely mill nonlinear wood and open up applications for this global material stream. At the same time, robotic arm systems are expensive, difficult to move. They have certain electrical requirements and other limitations. And so to democratize this workflow, we're developing a low-cost mobile robotic sawmill that will allow for widespread access to this tool to work with nonlinear wood and hopefully enable new species and new types of timber to be used. The technology will soon be applied in the construction of an installation for Exhibit Columbus. We call this project Sylvan Scrapple, using a bunch of different sort of waste woods coming together. And we're planning to cut nonlinear wood using this custom robotic sawmill to composite it into curved panels and leverage the natural quality of the wood that's coming together. So this is a sort of schematic model of this installation that we'll be constructing this summer to install in Columbus, Indiana next August.
So we've reached our final tactic, which is dialogue. We believe that to make an impact, we need to work together. And to this end, we recently co-curated the Biomaterial Building Exposition at UVA, which brought together scholars advancing a radical material future. Since its inception, UVA's academical village has been an architectural testing ground. The exposition expands this tradition, forging a path towards a material future that foregrounds environmental and human health, set against the backdrop of a UNESCO World Heritage Site. Architects from 5 universities were awarded grants and worked directly with UVA students from across the university to develop and exhibit full-scale installations at UVA. So here you see a map of the 5 projects that were exhibited across grounds, all the way from arts grounds to the physics building and the first year dorms, and then a kind of drone image of each of those 5 projects from above. A gallery show, including contributions from the School of Medicine and School of Engineering, framed a larger field. And finally, a symposium in the Rotunda welcomed experts to grounds and created a venue for cross-university discussion on this radical material future. Key to this dialogue are the voices of the next generation who will champion the climate future in practice. In core coursework at the School of Architecture, students are advancing material research, and their work is already making an impact and being recognized by professional awards. Architects today conceptualize and execute not just single projects, but also the systems, methodologies, and technologies that enable their production, with broad impacts on societies and ecologies. Leveraging this role, we hope to imagine and pilot a new material future. As this area is still emerging and there is much work to be done, we invite you to join us in this endeavor. Thank you so much.
Thanks, Kyle. That was great. We did receive a few questions ahead of time. We've gotten a couple questions during the program. For those that are joining us with questions, I'm doing my best to combine some of these questions together. There's a little bit of overlap, so bear with me. I'm trying to get to everybody. One and a half questions we've gotten from folks is, if you could share a little bit how you all got interested in something like this. You know, where did you all get your start? How did you get to UVA? That kind of stuff.
Sure. Well, thanks so much for the question, and thanks for coming to the talk and hearing a little bit about our work. We actually both met in architecture school, and we spent a lot of time in architecture school making beautiful drawings for our classes, but we were both really interested always in getting into the wood shop and the metal shop and making things with our hands. So we started just being, really interested in materials. And so as we kind of moved past, graduation, architecture school, the presence of the climate crisis what kind of always came calling to us. It's something that's kind of really hard to ignore at this day. My parents lost their home in a natural disaster. We've seen the kind of farmland that Kyle's parents work on transform in recent decades. And so the question of doing work that really engaged the climate future became important to us.
And so a lot of our early projects, like he said, we wanted to get our hands on real materials and make sort of real things in the world. So we got our start sort of through architectural competitions and public artworks, building and installing physical things, in cities across the country. And then we really wanted to kind of continue exploring kind of how do we actually fabricate with materials? How can we start to author the tools that are used to produce architecture, which is what sort of brought us to UVA and to kind of teaching and academic research. We have our sort of practice as well, and both worked in architecture firms, but we're really excited about the types of research that can happen. There are kind of risks you can take and things you can experiment with in academia that allow us to kind of really imagine the future kind of a couple steps ahead of the profession and pilot and test ideas that we hope could then be kind of taken into the profession, taken into architectural production. We have some things to figure out in terms of building code. That's sort of all in progress. But the hope is that this work then can scale up and hopefully have a kind of larger impact in the future in terms of how we produce architecture.
Well, it's interesting that you bring up, looking ahead and building codes and things to figure out. One of the questions we received during the presentation was actually similar. What kind of challenges, perhaps unforeseen barriers or challenges, did you all come across, maybe in relation to trying out different materials during some of your projects?
Sure. Well, I think there are a few challenges that we face with these types of materials. One might be from the side of code, though there's been a lot of kind of positive developments relative to code in the mass timber industry in the last decade, particularly in the Pacific Northwest, where there's been a lot of kind of bipartisan support for the timber construction industry. But also there's been a lot of kind of proof of concept of that work coming from across the pond. So we see kind of promising developments in building code. We also see kind of cultural perception as a barrier to the implementation of renewable building materials. Even though there's a long tradition of working with a material like bamboo, many people associate it with kind of temporary building structures. It works wonderfully in permanent structures and particularly in things like difficult seismic conditions, but there's just cultural baggage to overcome. And I think that's something that we're seeing with hemp as well. Now legislation is, making it possible to grow hemp in places where it wasn't able to be grown until recently in the US, and that expands possibilities for hemp in building construction as well.
Yeah, so it's almost like a kind of three little pigs question, right? Like the house of straw and the house of sticks maybe get blown down, but not the house of brick. But there's no reason that we can't make these materials, last in long-term construction. I'll also mention that a lot of the examples we showed today are sort of results of research grants that are sort of aimed at proving a single material system. But when we think about buildings, there are, nearly always a complex material assemblies where the materials that are kind of forming structurally in the building are totally different than the materials that are providing insulation, are different than the materials that are providing waterproofing or cladding or roofing. And so we like to think of these as like tests that could then maybe become parts of more complex material assemblies. And we're also always really interested in showing what can these materials do kind of performatively, again, whether that's structurally, thermally, acoustically, et cetera, but also what can they do kind of spatially, or how can we express those materials? Getting back to the like three little pigs question, right? Like how could we make a, a desirable, how could we sort of show people that like you could have a house that had grass as a material in it, and how could that be kind of beautiful and durable and possibly desirable as well? So there's a lot of work to be done, but these are the questions that we're kind of always thinking about as we're trying these different material systems.
Sure. I know you guys are big time and on the national on a national platform, but one of the questions we had gotten prior to the presentation had to do with permitting code framework in Virginia and Albemarle County, and obviously, I don't know if national supersedes everything, but I don't know if you all have had any dialogue with local builders here in Albemarle County and Charlottesville, or delved into local politics or the building code at all. If you've seen any wiggle room there, or any willingness to listen here around the university, where we all know as plenty of issues related to housing supply, for example.
I think that's work we'd love to do, and like conversations we'd love to have. We're relatively recent transplants to Charlottesville, having started our positions here in 2020. But now a few years in, we know UVA well and are ready to move beyond grounds in our work. So yeah, and anyone interested in collaborating or having those discussions, that'd be really excellent.
Yeah, I think the town and city are excited about this. I mean, so many people, locally care about the environment in a way that they're like invested in sort of new ideas. There's a beautiful mass timber building that was put up just between downtown and Belmont a couple years ago. So the kind of new technologies are here. And I think, yeah, we're interested to work with people locally, but also think about sort of things at the level of the sort of national building code, in terms of how do you kind of test these materials so that people know and are kind of convinced, and we know that they're kind of safe enough to use in various applications. So it's an ongoing process, but if anybody locally wants to work with us, we'd be happy to do so.
With that last point you were making, is there, beyond that, is there anything that you all need to explore in order to look at scaling up the use of these materials on a wider scale?
Yeah, definitely. So I think the way that we're thinking about scaling up right now is starting kind of from the beginning of the process of saying, how do we go from kind of a raw natural material, like a tree or a log or a bunch of grass, to a kind of building product or an assembly that could be used in building. And so that's things like the pillow forming system that we showed today, as well as the kind of robotic sawmill, which is hopefully going to be operational within the next couple of weeks as a prototype, so that we can kind of work with these materials, these natural materials, in a way that takes advantage of some of their different properties. And then there's a kind of process, I think, after that, that's going to be a kind of performative testing process. And we've worked with a bunch of engineers and other sort of disciplines at UVA in that regard, to look at like, how do we sort of know that things are going to perform structurally in a way that's predictable? Or how do we know that things are going to perform in terms of insulation, thermal insulation, in a way that's sort of predictable, and we can know their performance and think about how then would they perform as part of a kind of more complex material assembly within a kind of permanent building.
But certainly also, one of the reasons that we don't use materials like this more today is because industrial processes made working with other materials so easy and so cheap. And so when we're developing construction practices for these materials, we're always trying to think about ease and cheapness and time as factors. And I think scaling up production would continue, that those questions would continue to take on more relevance. Material systems really have to be affordable to a really broad public in order to make an impact, especially when we consider how much construction is going to go on, in the developing world in the next 30 years.
So there's two more questions I'd like to get to. Jeff from Atlanta has been very patient. He posted this question earlier, and I know he's still on. So Jeff, thanks for joining us. Jeff from Atlanta asked, we have a number of new residential pocket developments that utilize a farmhouse craftsman style and mostly have white siding finish and dark trim. And he was wondering if there's some thermal benefits, some other benefit, or is this just trendy?
Sure. Well, I love the specificity of the question, and I think it helps that you've told us you're located in Atlanta. I might speculate that the white siding is a way to deflect heat, since I know it gets quite warm there. So there certainly are thermal benefits to what color you choose for a building project in a particular climate. I do think that the rise of the kind of like farmhouse or craftsman style is maybe more culturally rooted, but oftentimes the kind of wood finishes feel more intimate or homey and have different psychological effects on occupants than, you know, materials that we have in other building types. So there are kind of both cultural questions, but there's also ways that materials affect our, you know, our mental health and well-being as well.
And that's one of the challenges, is again balancing that kind of performative quality of the material relative to the environment and other factors, as well as the kind of aesthetic quality. You know, what do people want? What do people like? What is a kind of comfortable or kind of friendly environment for people? And so we're always trying to balance those factors when evaluating what materials to use or how to deploy them in buildings.
Okay. Last question, and I'm going with this one because it seems a little topical. Do you foresee, this is from Jeff Looney, do you foresee using the same analytical techniques for reimagining building materials while using AI and machine learning to scale up the process of joinery and fabrication?
That's a really good question. So we've been, you know, playing around with these different tools for a while. I think a lot of the kind of explosion over the last year that we've seen in AI, especially with text to image generators, has been really amazing. And architects in general have been like so excited about it. There's a bunch of different ways to think about how those tools are used, I think. Some people think about them as kind of being sketching kind of tools right now, ways to kind of think outside the box, think of new ideas, to visualize those ideas. But we're really interested in how can these tools then be applied sort of more on the machine learning side to look at and understand natural materials. And so when we look at the kind of complexity of form of a log, for instance, we can kind of 3D scan and digitize that information, and then use these tools potentially to look at different ways of slicing this material to be able to produce elements that are then composed into architecture. And so the whole idea with this like robotic sawmill, for instance, is that we'll be able to cut wood that is not just sort of flat orthogonal pieces of lumber that could be curving, could be twisting, could have other variation to it. And so these tools are here, they're going to be used in the future. So I think that everybody should be thinking about how they're used. And we're particularly excited about how they could be used in imagining this kind of relationship between grown form and built architecture.
Yeah, I think there's so much potential in this area and really excited to get into it more. But when computer-aided design was introduced into architecture, it made coordination much easier, it made precision much easier. When parametric design was introduced into architecture, it made optimizing and iterating much easier. So you could generate a lot of different versions and test them for solar orientation or structural performance and things like this. And so those kind of tools are what makes, I don't know, working with the cookies actually go quite fast, even though each one is a custom geometry. It's not like we're individually doing the work for each cookie to decide its geometry. The computation is taking a lot of the heat off of us. And so I see a lot of the potential of AI is making coding and sorting and using tools like parametric design that much easier as well.
I did use ChatGPT to write my introduction for you guys, so it's making moderating a lot easier too.
Well done, well done.
So that concludes the webinar for today. I want to thank you all for coming once again. And if I could remind you that it is the spring challenge for the UVA School of Architecture. We hope you can join us in supporting the faculty and students who are working with Katie and Kyle on some of this amazing research. We do have a one-to-one match available for all gifts up to $50,000. So you can double your impact today by following the QR code here or looking in the chat one more time for the link. If you are interested in watching this webinar again and sharing it with your friends, the recording should be available soon on the UVA Club's YouTube channel. I hope you all enjoyed this as much as I did, and I hope you all enjoy the rest of this beautiful spring day. That will conclude the webinar. Have a good evening.